All right. Morning, everyone. Hello. We're at our usual Tuesday of emptiness, but I appreciate y'all being here. So yeah, we are the last week of content today. I already mentioned this, and I'll probably mention it a few more times. People trickle in. I've got 5x8 note cards up here, so if you want one at any point, just come up and grab one. There you go. So they're here. I'll bring them on Thursday as well. You don't need to go buy a pack of 100 just so you can have one of them for the test. I think I have a first draft of it. So, making a test, it's kind of like writing a paper. There's a draft of it, and then I go through and I double check everything and all that. So I think I have a first draft of your all's test. And currently the plan is 24 questions. Within 3 free response, pick 2 out of the 3. That's kind of where we're landed. 24 questions. The math works out really nice. Where, remember, 60% of your test, 60% of the grade is from the multiple choice. If you do 60 divided by 24, it comes out to 2.5 points per question, which means if you miss 4, you're still at 90, assuming you get all the free response correct. Yeah.
When's our exam?
Yeah, your exam is a week from Thursday. February 13th. So yes, if you have at any point, all the exam dates are on the simple syllabus at the very bottom. February 13th is our first exam, and then our second one is... I'm not going to quite say because there's spring break and that throws things off, and I don't want people to get mixed up, but it's in the syllabus. I want to guess the 27th, but don't quote me on that. Do not take that as gospel. Look at the simple syllabus to confirm that. And your all's final exam date and all that jazz. It is in, so the exam is in this room. You get the full 2 hours and 50 minutes. I'm going to send out an announcement sometime this week with all this in writing, just so you all have it. I will do my best to also generate a couple study resources for you all. Specifically, they're nothing crazy. They're literally going to be, I'm going to take the problem set problems and just mix them around. Like, nothing crazy, but one of the skills is, can you identify what type of, because the test is going to be all mixed up. The test is not going to be in the order you learned it, because that's not testing if you know what's what then. So the test is going to be all mixed up, so the problem sets will be mixed up. And I'll also try to go through and find all the all the top hat questions and put them in one big PowerPoint, also all mixed up. When I put them in this PowerPoint, they'll have all the answers like in the ink thing. But what you can do at the very beginning of if you download my PowerPoints, you can hide all the ink in a presentation just by clicking this. And then if you want to see it again, you just click it and it pops up. So I'm not going to make 2 versions, one without answers and one with answers. I'll just make one with answers and you just hide the ink and that'll hide all the answers. Okay, let's see. I think that's about that. Oh, yeah, that's what I mentioned. Grade-wise, so on a test, if you want an A in my class, basically what you're aiming for is an 80. And the reason for that is if you look at how the grade is broken up in the class, 50% of the grade... Oh, did I start the stream? I did. Good job, me. If you earn 50% of the grade in this class, it's like you do the effort, you get the points. The labs, the quizzes, there's something else chalked in there, the top hat questions. As long as you kind of do those things, you get the points. That's 50% of the class is just like you do it, you get the points. Great. The other 50% is tests. And so if you do the math, it comes out that if you get the free 50% of points from the beginning, you only need to average 80% or above on the exams to get an A in the class. Then you do the math. That means to get a B, you need to average 60% or above on exams. To get a C is 40% or above. The assumption, though, is if you're doing all the other things that, they would correlate well and all that good stuff. But so that's the structure. It's worked out pretty well for me so far. And so, yeah, that's the mindset going into the exams and things like that. Also, this first test tends to be the hardest test, not because the content is necessarily more difficult, but because you all are learning physics while you're also learning physics skills. So the skills that you all are learning right now, vectors, breaking things, the problem-solving process, learning how to draw the pictures. One skill that I've kind of realized that I need to make maybe a bit more explicit is identifying what the problem is, when the beginning of the problem is, and when the end of the problem is. That's been a really common challenge I've seen is is something the initial or the final? And so for that to happen, you have to realize what the problem is. Like when you toss a baseball, I don't have my baseball anymore because I don't have my jacket. It's very sad. If I toss my water bottle, I'm not going to toss it. I made this mistake before. There's like 3 problems involved in tossing a water bottle. When it's in my hand getting pushed, that's its own problem. Once it leaves my hand and it's flying through the air, that's its own problem. And once it hits the ground and does a bunch of things, that's its own problem. I've seen a really common thing of like when you're pushing something through the air, when someone's like throwing something, they'll say the initial velocity is 0 because when it's in my hand right now, it's 0. But we're not actually considering that part. We're considering always projectile motion when it leaves. Anyway, so that's a skill. When does things start? When do things end? Where's the actual boundaries of my problem? Yeah.
I was wondering, are we able to view our exams after we take it, like what we got right now?
You are. So the week following exams, my office hours are kind of makeups because I have people that have emergencies that arise and things like that. So those office hours are for that. But after that, my office is kind of where if you want to see your exam, what you missed and all that stuff, that's where I do that. I don't post the exam because making these exams takes a large amount of time. Making a problem that is fair, no typos, accurate representation of what I've asked you to do. It's really hard. Like it takes many hours. And so I haven't figured out an elegant solution to that. But yeah, the solution I have found, if you want to review your exam, you're more than welcome to after. And in your grade book, there'll be 2 grades, one for the free response, one for the multiple choice, so you can kind of see how you did on each portion. And yeah, if you come by my office, I can show you which ones you missed and all that jazz and show you all the answers and all that good stuff. Yeah.
Are the test questions more like the homework quizzes that we do or like the practice problems?
They're going to be more like the quizzes because they're problems I actually wrote. So all the problem set problems are from OpenStax. And so they're a little bit more wordy. And the reality is I'm not going to put a paragraph of text because I don't have space in the test to fit that many questions. Like I don't want you all to spend a lot of time reading. The quiz problems are ones I made. The test problems are ones I made. But they're based upon when I make these problems, I'm looking at the problem sets and things like that.
That's one more thing.
Yeah.
The short answer, are they multiple part
So
questions like the problem set?
no, so the free response, that's a good question. The free response is, so there's 3 questions that you can pick. No matter which one you pick, there's going to be 2 questions within it. An A and a B. And those will each be their own problem. And basically, no matter what you pick, one of the parts will be involving kinematics, and the other part will be involving forces. Like no matter which one you pick, and that's because the idea of this test is I'm testing kinematics and forces. So no matter which of the 3 you pick, you're still going to be tested on do you know kinematics and forces, but they'll have different paint jobs and different contexts and things like that. And you'll just pick whichever 2 you like the best, whichever 2 you feel the most comfortable with.
Are there like questions A and B going to be set up like you have to be able to solve A?
No, that's a great question. So the way these are set up is I've done my best, and I'm pretty, like, A and B are independent. They're still going to reference the original problem in some way. So they're still using the same context, and there might be some givens that carry across both of them, but you will not use the calculation from part A and part B, because that just makes grading a pain. And I also don't like double penalizing things. So no, part A and part B are independent with the exceptions of like some givens from the original problem, some givens might be the same in both. Yeah, but no calculations or anything won't transfer.
If we do all 3 problems for the free response, we do choose which 2 are best.
So if you do all 3, you'll still need to mark 2. And then the grader, which may or may not, I will take a subset of the tests, and then Peter here will take the other subset of the tests. I take a subset to be like a standard in some way. So like I go through them and see, it also gives me a sense of how you all did. We will only look at the unmarked one if it's perfect. So we'll look at it. If it's perfect, great, we'll give the points for it. But otherwise we won't, just because it adds an extra 100 questions to grade, which then delays grading and all that jazz. So yeah, that's currently the philosophy I have. Grading a perfect question is really quick. So we'll look at it. If it's perfect, great. If not, we'll use one of the other ones. And the rubric for how partial credit is assigned, that's in the formula sheet if you all haven't seen that. It's the problem-solving process. If a picture was relevant, did you draw a picture? Did you write down your givens? Did you write down what you're solving for? Did you write down the relevant equations? And then how did it go when you were plugging things in? And you will get 80 to 90% of the points. If you mess up, like you put the wrong number in the wrong spot on accident or calculator error, you'll get 80 to 90% of the points. If you accidentally mix up one thing in the beginning, but your process is largely good, you'll get like 70% kind of like you'll get most of the points if you know what you're doing. If you make a silly mistake somewhere, it's not going to ding you that much. So keep that in mind. All right. Again, I'll send out an announcement with as many of these details on the test. You just need your 5x8 note card, any calculator you want, a pencil, ID, and that's it. Oh, and if you have accommodations through Student Accessibility Services, please make use of those. Again, we'll have 2 hours and 50 minutes in here, but I always encourage people, if you have the accommodations, like I want you all to take advantage of those. I'm really glad those services exist. Quiet testing environment, all that jazz. That's it. All right, it's going to be a great time. So much fun. Again, the first test is always the worst just because you don't fully know what to expect. So it's okay to have that, like, I have received, I can't even think of any. Generally, I have not received really much any complaints concerning that the test didn't look like what the preparation stuff does. So when I get I'll ask for feedback. There'll be a feedback form I'll send after the test. I almost never, I can't even think of any feedback that, the test looked different than the practice. That doesn't mean you might not feel that way, but it just means at least I don't hear that. And usually you hear that in SPIs at the end of the semester or these feedback things. So, give you all some peace of mind. If you're doing the stuff, it will pay off. If you're studying it, preparing for it, all that good thing. Okay, so today we'll probably get through forces, if not all of it, a lot of it. There might be a little trickle left that we do on Thursday, but really we should be able to get through a lot of it today. That'll give you all a good amount of time to kind of then practice and all that jazz. Before that, we got the joke of the day. I'll let you just grab your own. That way if you ever... What? Yeah, get your own microphone. Yeah, that way if you ever need it.
It's like done. Oh. Yeah.
Hit the button so it turns green.
Does that, okay.
It does.
So, the maintenance guy lost his legs on the job. Now he's just a handyman.
All right. So, let's see if y'all remember normal force. I'm not going to say anything. Just read the problem. 100 kilogram person wants to jump. What does the normal force need to be for the person to get off the ground? Is it greater than 100 kilograms, greater than 980, less than 980, 0? I'll do this problem, and then I'll do a recap of what we covered last class.
The answer I had before.
It needs to be greater than gravity, but maybe I guess
That's what goes to high school. We're using it for
otherwise 980.
500 times per
Oh, then yeah, I'm good with how we
Big note card.
We're getting so lost. The same thing, actually.
As far as could goes with the way to take
Basically, like reassuring us not to worry.
It's the name after the dude.
Talking about
This guy discovered.
where you how to
Yeah, that too, but dude discovered forcing pressure. So we got to find
there's one question where he was like
what happens.
yeah, real.
Let's say let's do smaller than doesn't necessarily mean I think so.
Free body diagram. If you're unsure, draw a free body diagram. Remember, every force problem, that's always like a go-to. That's what we're going to be doing every single problem today. Free body diagram, free body diagram, free body diagram.
Yeah. So I know you make your own exam, for example. You get the two exams, you'll finally end with the same.
Also made by me. And everything is made by me currently. Maybe one day we'll have some alignment, but it's really difficult to get to because professors
Isn't it for chemistry they have like a ACS exam for like?
yeah, no, we don't have a standardized exam.
As long as you write the problems for the class,
Yeah, I kind of have some things, but yeah, I need to look at this guy.
Also another question too. If you don't have enough time,
Oh, we're gonna do fluids. I already kind of weak. Yeah. So I'm gonna replace this with some gravities. So I started looking at that. Yeah. No, it's because it's on. I think it's on. Like in the physics section. Yeah, I think fluids is a subsection of it, but also there's a lot of really interesting relevant things. Blood pressure and things like that.
yeah, physics just need I just need to know physics in general. And some physics too.
Is it not that much physics too?
It depends on the MCAT. It depends on the year.
All right, 20 more seconds. Which is probably overkill, but
No, there used to be.
all right, Peter, you want to explain this one?
Sure.
Huh? Oh, they always need explanation. Yeah. It's always good to go through. Draw the free body diagram, go through the things, and then I'll do the summary of like what we did last time. Here's a mic. All right, 5 more seconds. 5, 4, 3, 2, 1. All right, and something we're gonna do is I'm actually gonna have Peter and Sophia moving forward. They might do random explanations for you all because it's good to see it from different people. I present things in a certain way. It's good to see how they're gonna explain it. So anyway, you might see that time to time. There you go.
All right. So, is this working?
If it's green, it's on.
It is not green. Now it's green, I think. Now does it work?
This is also the fun of teaching is technical problems. Then you just try another random one. There you go. No, that
Okay,
one.
this one works. Good. Okay, so if someone wants to jump, forces acting on them are going to be gravity and the normal force. And so if you draw a free body diagram, you have, it's a horrible square, force from gravity and the normal force. And if you want to, that's terrible. How do I erase?
Oh, the back of it. And the you can put your hand on it and it won't draw, so you don't have to worry about that.
There, now you can actually read that. So if you want to accelerate upwards, the normal force is going to have to be bigger than gravity, and the force from gravity is going to be m times g, which is going to be 908 newtons. So the answer is going to be B.
No, not D.
I said B.
B. B is in boy.
Yeah. So, yeah. That's it.
There you go. So, reminder to y'all. So then now this will give us a nice recap of this problem. Basically, almost recapped kind of what we did last time. The name of the game, y'all, when you do force problems, if you see the word force in a problem, that is a trigger that you immediately should follow the following process. Draw a free body diagram. You're going to do that. Like, if you do not do that, it will go south for you. And that before you do any numbers, who cares, like, what the numbers of the problem are? Draw a free body diagram. What is pushing and pulling that object? In this case, there's gravity, and they're on a surface. So that's the normal force. All right. The next thing you're always going to do, you're always going to set up the sum of forces in the x equals max, and the sum of forces in the y equals may. You're like, this is always, even this problem, you're like, I might not have done that. You secretly did this. Like, this is secretly behind the scenes in every single problem. This is how you do force problems. So kinematics, you had to choose the right equation. You had to write down the givens and the missing and find the right equation. We're still going to do that. But in this case, this will pretty much always be your equation. Like, guaranteed. These are the equations you're going to use. It's going to happen. But you have to build the equation. Forces, you have to actually build the equation. Whereas kinematics, you just look at it and wrote it down and plug stuff in. All right. Are there any forces in the x direction in this picture? No. So, great. 0 equals 0, right? 0 equals m. Oh, what's my acceleration going to be? It's going to be 0. Yay. Like, obvious. But, again, I put both directions here just to get us used to it. And the y direction, y'all tell me. What forces are there in the y direction? Gravity and normal force. One at a time. Normal force, is it positive or negative? Why?
Because it's going up.
Because it's going up. Great. Gravity. Positive or negative? Negative. Equals m times a in the y direction. You're secretly doing this for you to jump. What does your acceleration need to be? Positive or negative? Positive. I don't care what number it is. It needs to be positive. If this needs to be positive, then the normal force has to be bigger. You have to have a bigger positive number to get a positive number. And so that's the logic in this problem. Yeah. Normal force will always be going away from the surface. So in this problem, we assume the ground was flat. That's a very reasonable assumption to make for almost any problem. You will know when the ground is not flat when I say we're on an inclined plane with an angle of this or this. So the normal force is always away from the surface. So eventually, we'll do inclined planes, in which case the normal force is away from the surface. Also, if you're leaning against a wall, if an object is leaning against a wall, then the normal force is going to be away from that surface as well. So if you have a wall and say something is leaning against it or pushing against it, say like you're doing a rock climbing. You're climbing a wall and you're holding on to that, or you're rappelling down a wall, the normal force will be away from the surface. Normal force is always away from the surface. Whatever.
I was just gonna ask, do you have to do all those steps you did after to get full credit?
No. So this would be a multiple choice problem.
Okay.
And the multiple choice, I don't check any of your all's work because there's 24 questions. So multiple choice is all or nothing. I don't care what you write down. There is multiple versions of the exam. And the reason for that is so that, because it is all or nothing, I don't want to make it super easy for someone to look over and just, someone put 14C, so I'm going to put that. So that's how I get around that. But no, multiple choice, it's all or nothing. I don't care what you put. Free response, you're going to almost need to go through these steps to make sure you don't make a mistake anyway. So it's to your advantage in two ways, to get the right answer and to get the partial credit.
If the force is at an angle like that, you have to break it down to x and y. So that's a foreshadowing of what's to come. It turns out when we do this inclined plane, we're not going to, great point. Do we need to break it x and y? Yes, but ironically, we're not going to break that one into x and y. We're going to break gravity into x and y. You'll see that it's easier you basically have to break something into x and y, and we'll do gravity because then we only have to do one vector, whereas if we did the others, we'd have to do multiple. So yes, we will have to break these into x and y. All right, and there was another question, I think. Maybe. All right. But yeah, this is the summary. Basically, every single thing moving forward is draw a free body diagram. Draw the forces on it. That is a free body diagram. Sum of force in the x equals max. Sum of force in y equals may. Build your equation from your picture. Add up your forces in the x. Set it equal to max. Add up your forces in the y. Set it equal to may. And we did some problems with the elevator before with this. And you're going to notice every single slide, free body diagram, like it's everywhere. But yeah, these problems, the process is fairly set. Draw a free body diagram, set up that equation.
But the challenge here is it's not just write down the equation and plug stuff in. You got to build the equation yourself. There is no equation on your formula sheet that says Fn plus negative Fg equals MAY. That's not going to exist. You're just going to have sum of forces equals MA. You have to be able to build it. That's the skill that you're going to be doing with forces. Okay, so now I just introduced more forces. Tension. Any rope-like object. The force in a rope-like object. Rope, thread, cable, chain, string, strap. I'm trying to think of all the things that could possibly count as a rope-like object. Whatever this thing is, I guess it technically can. Do we assume it's a rigid string, that it can't be stretched? We're going to say, I don't think it matters. Maybe it depends on the problem. But anyway, don't worry about it. If there's a rope in a problem and it's pulling something, it's tension force. There is no equation for this. It's literally just, a rope, a chandelier is hanging from a ceiling. Find the tension force. That's the rope that's holding up the chandelier. So, there's a lot of ropes and problems, so they get their own fancy force. I put the variable here as tension. You can either do tension or you can do like force lowercase or like subscript T, whatever, however you want to do it. I will try to do this like F and then subscript notation. I think I like that one the best because then everything's forces and you just put an adjective next to it saying what type of force it is. But if you like capital T, that's fine as well. And yeah, no equation. You either calculate it using F equals MA or it gives it to you in the problem. All right, nothing really exciting there. Nothing really insightful. All right, great. A 20-kilogram chandelier hangs from the ceiling. What's the tension of the wire holding up the chandelier? It's going to be shocking. The first step, draw a free body diagram. Do the process. Like it's the same process again and again and again, which is great. And we're just looking at the chandelier. When you choose a free body diagram, you have to choose what you're looking at. Draw a free body diagram of the forces acting on the chandelier. Just the chandelier. Oh, I will send the question to you. Ka-chow. Nope, wrong one.
Going this way is this way up. So probably down.
Which way will gravity pull the chandelier? Up or down? Yeah. That was just think through which way is it pulled. So that's all the forces. And so the normal force here is only on the surface. So there'd be a normal force. There is something pulling it up. What's pulling it up?
It's not like the rope is pushing us up.
The rope? What do we call the force to the rope? What is the force doing?
So normal force is
It's only there if it's on the surface. Yeah. The second you're no longer touching the ground, normal force disappears. The second you no longer leave the wall, normal force disappears.
But there always has to be some sort of force mechanism or consuming gravity.
If you're on Earth, there's always going to be gravity. And then if it's not accelerating, and if it's not accelerating, something must be translating. Yeah, that's a great point. But if you're in space, there doesn't have to be gravity. But pretty much everything's probably the same. Right. Beautiful picture. Alright, what does that arrow correspond to? Alright, so if that's the only force acting on it, which way should it accelerate?
That is a little scary, actually.
Why is it falling? The wire. Which way is the wire pulling? So we call the force of the wire. And a wire and a string. So there's an arrow that you're going opposite ways. Yeah, so we did the pulleys on this trick. Basically rotates. That's what a pulley is. Force goes down. And so we're going to basically look at every problem. Pulley is a one-dimensional. As crazy as that sounds, even if you have an arm like we're going to do a pulley hanging from something, even the ones where right going up and down, the reality is that you're only doing four. There's no one direction. So we're basically going to say a pulley redirects. So it's as if the pulley is pulling that anyway. So we can find the acceleration of the system by basically looking at that screen right there and they're attached to each other. In that case, the block is right. And then we can then go back and look at just one of them and say, oh, now we go to acceleration.
Well, like, do you have to make an assumption, like, if one has a greater mass, you would assume that one probably has to go down?
Nope, they'll go through together. That's the cool thing, they'll share these. Yeah, so we'll do those problems.
That'll be the kind of end. All right, 10 more seconds.
You want to do this one? It's good practice. Do it. Yeah, go through the same process. Draw a free body diagram. No, this is just the wires. Yes. I was like, do you want? I can do that. Okay. Yeah, this one. The tension straight up. The gravity straight down. Oh, it's tension. It's tension. Yeah, normal force is only when you're on the surface. Yep. Yeah, you did great.
All right, in 3, 2, 1. All right, great. And share the load.
Sophia's gonna do this one.
So it's pretty much the same as the last problem. So you're going to draw your chandelier, and then since we're on Earth, gravity's acting upon us, so we're going to draw an arrow down. So that's gravity. And then because we have tension coming from the rope that's pulling on the chandelier, we have another one pointing up, but instead of this being the normal force, it's actually the force of tension. So we're going to label it like that. And then it's the same math, so just F equals M times G, so F is equal to 20 times 9.8. And I think this was B. What?
That's gravity.
Yeah, so then how does that equal the tension force?
Wait, what?
Set up the sum of forces equal to that.
Assemble the what?
The sum of forces equals to that.
Oh. How do you delete? Wait. Here.
Oh, if you want the eraser, just the back of the pen.
Oh. Fancy. Okay. So, sum of forces. Wait. Just sum of forces is equal to MA?
Yeah.
Okay. So then that would equal. Is that good enough? I don't know if I did.
Yeah. I was like, the only thing So yeah, we got our forces here, and then it all boils down to the same thing, y'all. You sum up the force equals MA. The only thing here is, what's A? Yeah, is this chandelier flying up and is it speeding up or slowing down? I mean, look, there's That projector is a chandelier, effectively. So is that one. So is that one. They're not accelerating. It's not a trick question. If something is not moving, reminder to you all, acceleration is not velocity. Acceleration is not velocity. So it's not that it's not moving. Yes, that is true. It's not speeding up or slowing down. This chandelier, you don't need to worry about it speeding up into your head at any point or anything like that. So this side's going to equal 0. And then we build the other side. What dimension are we in? X or Y? Ooh, I hear 2 different ones. Up, down, or left, right? Up, down. So that means that's going to give us the Y. That's good. That's good. That's like, these are the questions that I'm glad to ask, that we're working on. So we'll just put little Y's here. And then, what's pointed up? Or, FT, up or down? Up, positive or negative? Positive. FG, positive or negative? So, Sophia did a wonderful job here. She found us that force of gravity. You just plug it in. And again, this might seem tedious. You might be like, why do all these steps? Because whether you like it or not, this is what you're doing. Whether you're doing it in your head or writing it down, you're still doing this. So by me writing it down, I'm showing you what you might have intuitively kind of seen. And then you can see that the force due to tension is that positive 196. It's not always going to equal the force of gravity. In this case, yes, the thing's not moving. But what if instead it was what if it was accelerating? Then you'd have to go through the steps and all that jazz. So Ft equals positive 196 newtons. And there you go. Just like identified. So, I got some good questions about, and I saw some people put this as a normal force. So this is where a distinction comes in. Reminder to you, a normal force is due to a surface. So if the chandelier was resting on something, either sitting on something or leaning against something, normal force. In this case, though, it's a string, so it's tension. Other thing I want to mention is when you are drawing this free body diagram, one way to check your work is just remember, does it make sense? If you drew this as your free body diagram, I don't care what this object is, what's it going to be doing? If force of gravity is the only thing acting on it, what's it going to do? It's going to accelerate in which direction? Downwards. Think through what your picture represents. If you only put the force of gravity downwards, it should accelerate downwards. Is my chandelier doing that? No. Okay, why not? Something must be pushing it upwards. What's pushing it upwards? These are the questions that should be going on in your head. A lot of physics is teaching you to ask yourself the right questions. That's all the logical process is asking a bunch of questions to yourself and finding the answers to them. Yeah.
On like the exam, if we were asked to find it with a different rate of acceleration, would that be given to us, or would
I would have to give it to you?
Stuff be given to
Yeah, it's a great question. So the question was, if I said if it was accelerating, what would you do? What would I have to give you? I'd either have to give you the acceleration or a way to calculate it. Yeah, you cannot do this problem unless if there was an acceleration that's not 0, I either have to give you it explicitly or have you calculate it. Like, something moves this fast in this amount of time, like goes from 0 to this in this amount of time, and go from there. All right. So shock and awe, it's the steps I've been saying, but now it's in words. This is how you solve all these force problems. Draw a free body diagram. Sum of forces in the equals ma. X and y are independent. If it's not moving or moving at a constant velocity, if something's not moving, it's not speeding up. Did weird things happen? What did it do?
Weird happened with the mic.
Oh, great. Maybe I was like, it shouldn't have picked up interference from another room. That'd be spooky, but anywho. F net equals sum of forces. This last one is a foreshadowing of things to come. If multiple objects move together, you can consider them together. So there's a couple of cases of this. There's a problem in the problem sets that's a dog, a bunch of sled dogs pulling a sled. That one is good. It does require you to make some assumptions that you might not realize. It's a good problem. I like that problem. Fun fact, ChatGPT doesn't get it correct. So if I have time, I'll actually do that one on Thursday. But it's good. I worked through it with a student and had to realize what assumptions, and they are good assumptions, but they're ones you might not realize. But eventually we're going to do a pulley problem. If two things are
held together by a string, they're going to share the same acceleration. If two things are linked together, if one accelerates a certain amount, the other one is also going to accelerate a certain amount. Because every problem we do involving strings, that string is going to be like tight. And so if one object moves, the other object moves. If you're in a car and that car accelerates at 3 meters per second squared, you will accelerate at 3 meters per second squared. If there is a trailer attached to your car and your car accelerates at 3 meters per second squared, your trailer will accelerate at 3 meters per second squared. If it doesn't, you left your trailer behind. You have everything that's connected together will accelerate together. Otherwise, there's some unbalanced forces and things might break. That's pretty much the only case. That would mean your trailer hitch is going to snap on you if those aren't the same, and you'll get left behind. So we're going to see that near the end when we get to pulley problems, especially. So anyway, mention it now. The more I mention something, the more likely it is. All right, this problem. I like this problem. Find the tension in each of the 3 cables supporting the traffic light if the traffic light weighs 200 newtons. Now, you do need the picture for this. So honestly, the picture is all you need to solve this problem. The words just describe what's in the picture. So I'm going to zoom in on that. And to solve this problem, you're going to have to break it into 2 parts with 2 different free body diagrams. So what I want you all to do before doing any math is I want to practice that free body. Can you identify what those 2 parts are going to be? Before we do any math, I want you all to try to draw the 2 different free body diagrams. And to know where you're drawing, so like I'll actually reference them on the picture. You got to pick a specific spot in the picture where you're drawing a free body diagram. You're going to draw the free body diagram of the forces acting on this spot of the picture. And then you're going to draw another free body diagram where the forces are acting on a different spot in the picture. And the things you pick are the things that you know the most information about. So, and then have what you need. So anyway, try that out. See if you can pick the 2 locations. And then draw the forces. And then after we draw those, then I'll cut you all loose to actually do things.
And then like you do the T1 and so that makes sense. Unless you do, because I was like, you could do T1 and T2 in regards to that surface. And
Grab one of these instead, because this is cheaper. Yeah. No, I'll try to give you more heads up on problem this time or something. That way you get that. No, I do too. Yeah. I've already done this problem in the past, so I have that context. But yeah. So what does it say that 200 corresponds to? So wait, what's it? Force of gravity is.
oh, okay, so that's already.
Weight is the force of gravity, and you can see that from the units. It's newtons.
Okay.
So it's a force step. Yeah, weight is the force of gravity. Same exact thing.
Okay.
Yeah, that's it. The pictures you drew correctly. So.
And then I
Yep.
drew 2 pretty right.
All right. So the first question is, what do we know? There's actually only one thing in this problem. There's only one force in this problem we actually know. Which one is it? Force of gravity. So we should probably pick the object. We should probably draw a free body diagram of that object, considering that's the only thing we know anything about. So the traffic light is going to be our first free body diagram. That's our first one. We're gonna draw the forces acting on the traffic light. So looking at that traffic light, you all tell me what's pushing and pulling it. Gravity. Which way is gravity pulling it? Downwards. Now, what's interesting, we normally label that as force of gravity. What's another name for force of gravity? There's another name for it. Weight. Weight and force of gravity are the exact same thing. That is the reason you go to space. What happens to your weight? It goes to zero because your force of gravity goes to zero. Force of gravity and weight are the exact same thing, and you can tell that by the units. What are the units for weight in this problem? Newtons. What's the unit for force? Newtons. So, great, we got a force of gravity down. Is that the only force acting on this this light thing? Now, what else is acting on it? Tension. Which one? I got 3 different ones. Which string is attached to it? String 1, string 2, or string 3? 3. So that's the one that's affecting it. Which way is that tension 3 pulling it? Great. That's our first picture. Fantastic. What's that? So that's going to let us solve. You can see from that. Is there anything pushing it left, right? Let's just make sure we're good here. No. Anything else pushing or pulling it? No. All right. Great. That's going to let us solve for tension 3. The second one. What's our goal in this problem? What are we even trying to do in this entire problem? Find the tension force of all 3. Will this first picture let you find all 3 of them? No, so you all are going to have to draw a free body diagram somewhere else in the picture where you then have information. Maybe you find it from the first picture, and then it lets you solve the second. So anyhow, I'm going to let you all see if you can figure out where that second picture should be, and I'll go around and kind of work with you all. Now that you have the first one, the first step is oftentimes the hardest step. So I'll let you all see if you can draw the second one, and then go ahead and do it. We'll go from there.
I think that was what you meant. But then what do I name? Are these both
Where does it correspond to your picture?
So would it be F T3 and then F1?
You found the mass.
Yeah, I found the mass. I just did it because I know I can make me feel better.
Because that's the two.
Oh, it's
Up to the right. That's where you're going to draw.
would it not be
You're going to
that?
draw them exactly.
I would say they're being equal.
Ropes always
Yes.
hold the spot.
Because it's holding it up.
Oh, we're going to assume this rope has no mass. The rope has no mass. That's going to... You don't see why that's important.
I mean, yes, I see that. Sorry.
We should know that the y-axis is
I mean, like these rays are the angles because this is a rectangle, so all those
Yes.
T3 is 200.
you can't say that. So,
Yeah.
but I don't think I mean, we
All right. So the second part of our picture is where we know information. So picture 1, we can find T3. Now that we're going to do that, you can find what T3 is. Fantastic. Once you find T3, that'll be a number. I'm going to let you all find that out. Where is the next place in our picture? Now that we know T3, again, you'll do that eventually. Where are we going to pick in our picture to draw our next free body diagram?
So that's what I
Right here, the intersection of those three. So that's what we're looking at. What forces are acting on that intersection? T3 is pointed down. When you look at this spot, you ignore everything outside of it. You are only looking at kind of what's around it. You pretend like that traffic light doesn't exist anymore because as far as it's concerned, there's a rope there, not a traffic light. So T3 is down. What else is acting on it? Which way does T1 point? Up and to the left. T1. And we're going to put our angle here because if you haven't realized it, these are vectors. Guess you're going to have to break things into components. And T2, which way does that point? Up and to the right. And same thing, I'll put the angle here. All right. You've got your free body diagrams. Do one at a time. Do one at a time. So we're just going to look at the first one. Pretend like we're just setting these up so that you all can start going through this process. Pretend like the second one doesn't exist. Pretend like that doesn't exist. Find T3. How are we going to do that? So you all have the weight. What are we solving for? T1, T2. So just to make certain we're going through these processes. But remember y'all, every single force problem boils down to the same thing. What equation are we going to use? F equals ma. The sum of forces in the x equals max. The sum of forces in the y equals may. You need to do that for both of these free body diagrams. Do one at a time. Do the sum of forces for the first picture. Find T3. Then bring that to the second picture. Oh, there's one more given I didn't write down here. It shows up in this equation. See if y'all can tell me. It's one that you're gonna know it when you need it, but just to make it explicit. We do know gravity. Sure, we can check that in here. And then there's one more. The acceleration. What's the acceleration of my light? 0. What's the acceleration at the intersection of those strings? 0. The acceleration in the x and y is 0 at every point because they're all connected. If the acceleration is 0 somewhere in that system, because they're all connected and nothing is swinging around wildly, the acceleration everywhere is 0. The last thing I mentioned, remember I told you all these ropes have no mass associated with them. The reason I said that is because if they did have mass, in that second free body diagram, you'd have to have a force of gravity. Because the ropes would actually pull things down and all that jazz. But they don't. Every single problem we ever do, these ropes do not have mass. Because that would be a really unpleasant problem to solve if they had mass. So, there you go. Try it out. We'll go around. The first one's pretty simple. The second one will be a fun time.
I was trying to figure it out and just think logically because we're not doing the numbers, so we can't really use the color to figure out. But I found
I just want to make sure that I
Did you do the x and the y?
this is going to be 200 obviously.
T1 equals
So these
T2.
would have to also
T1 sine 41 plus T2 sine. You're doing the y components? Equals 200. Yeah, minus 200, and then you move the 200 over.
Yeah.
Because it equals MA, and so you subtract that over. Good. Yep. Whether or not these are the right answers, I don't remember, but your process is good. Yeah. They end up equaling each other. Why do these equal each other? They are in equilibrium. What's the acceleration in the x direction? Yeah, so it'd be T1. This one would be positive minus this one equals 0. So then it ends up getting added to that side. Just to fit within that logic of sum of forces.
It would be because these are being added together equals 0.
Yeah. And this, because this one's negative because it's the left. That's, yeah. And just to connect the two, it's always sum of force equals MA. You're always doing that.
And it ends up showing that. Hello.
I'm confused because so I made it so we had a net. So a net force is the force of tension plus your force of gravity, right?
For the equals.
I mean, we can figure out the angles.
Your mass is in kilograms.
We're not good.
You don't know the math. So here's the cool thing. What do you know? The A is 0. A is 0. You don't even care about this. So that happens. What's your force of gravity?
Oh, well, yeah, that was so long.
So that's the acceleration.
I think I know this.
The weight is the force of gravity. It gives it to you probably. So it says that the weight.
You can do it with only having
The final weight.
when you write it out, it's like the force of gravity is.
Force of gravity is weight.
And then you just know it's like,
And this makes sense. Attention equals force of gravity. For the same else to move, the string has to pull up. It's have to do not gravity. So again, the logic all.
yeah.
Yep, and the math all reflects that. No, upward is always positive. Up is positive, down. It is, it's, yeah, but it is negative. Well, you're adding, you add the negative.
Well, I think it's 11, right?
Yeah.
Because which way is the point, up or down?
No, I think it's
Up is positive, down.
So that makes sense though, because
Wait, you're right.
All right, so let's work through part A. I'm seeing enough people confused on. Let's do the first one. Let's build the first one. And it's okay to be confused. Like the fact that many people are confused means that, yeah, we want to spend the time on it. So I'm only going to copy and paste. Copy and paste the first part because we don't care about the second. We're just doing one at a time. So let's build the equation. Let's build the equation for it. So let's look in the x direction. The x direction, is there any forces acting in the x direction? No. So look, I'm not going to write that one at this point. I'm just going to stop writing it if we don't need to. Sum of force in the x equals max. There is none, so who cares? Don't care. What about the y direction? Yeah. You tell me what's acting in the y direction. Let's build the equation. Let's sum them up. What forces are acting in the up-down direction? Gravity. Which way is gravity? Up or down? Down. So negative Fg plus. Any other forces? Tension. Any other forces? In this picture, any? Yeah, we'll look at one picture at a time. There is, and this is the reason free body diagram. It lets you go through, did I write them all out? No, that's all of them. That's the only forces. Equals. The right side, mass times my acceleration in the y direction. Now you put in numbers. What's the value of my force due to gravity? Ooh. Yeah, so this is the question. Is it 9.8 or is it 200? So this is a reminder to you all. The force of gravity is m times g. But in this problem, do we know mass? No. Oh, man. How are we going to calculate it? There's a given in our problem, which is weight. What is weight? Weight is the force of gravity. So and it's in newtons. So my force of gravity is negative 200. Do we know T3?
No, that's what we're saying.
Leave it as T3. Equals? Do we know the mass? No. How sad. Oh, man. How are we going to solve this problem? We have two unknowns. What's my acceleration in the y? What's going to happen to... Ta-da! And you find T3. So this is the problem. You always are building the equation. You're always building it. Every single time in every single one of these problems, you draw the picture and you build the equation. So you solve for T3. I'm going to give you all a moment for that. And then I'm going to help you all set up the second one because that one's going to be A fun algebra problem.
Like that.
How to do it?
T1 and T. Like I know how to do like the math.
You always break it in. Yeah, you always break it into components, and we always then write those components in terms of the thing. That's just always the strategy.
So like there's no way like
That is kind of the recipe. Is you'll write T1x, T2, but you always will write those in terms of the original. Like you always write those in terms of the T1 and T2. Yeah, that's just you always end up doing that.
But like what I mean is like the math behind it is there like a specific explanation as to
Yeah, sum of force in x equals max, sum of force in y equals like we're gonna use that.
yeah.
Yeah,
So
we're just gonna build that.
Okay.
Yeah. It always comes down to that equation. All right, so this problem was hopefully mathematically very easy. What's T3 equal? So negative 200 plus T3 equals 0. T3 equals positive 200 newtons. Yay! It's upwards. It's positive. Life is good. We got one of the forces. That was the easy one. All right. Now we're going to go to the second one. And the second one is going to be algebra funness. So now I'm just going to copy this one over. Doop. Doop. Copy the picture over because we need the picture. All right. Immediately, you all see things. If you all see angles and you all see vectors, what do you immediately know you're going to have to do? You're going to have to do trig. That should again be one of those flags. You're going to have to break them into components. Like, that's just your brain should immediately say, I'm going to have to do this. So before I do anything, let's just do it. We know we're going to have to. Let's just do it. And then later on, we're going to see that why. We're going to see the reason why later. But that should immediately be a flag to you all. I need to find the x and y component of 1. I need to find the x and y component of 2. Now, you're not going to be able to find the values of it, but you can at least write the expressions for it. So, draw your triangles. And what I want is T1x equals T1y equals T2y equals T2x equals. You're not going to be able to get numbers for these, but you will be able to get expressions. You'll be able to get them in terms of T1. You'll be able to get in the magnitude of T1, and you'll be able to get them in terms of T2. Practice this. Try it out. Just know that you're going to need to do it. Before I even do any setup, this is a flag that you're going to have to do it. If there's angles and vectors, that's a flag. You'll leave it in terms of T1, and you'll leave it in terms of T2. Yeah. So a variable is just a number you don't know yet. You don't know the value of T1, that's fine. Leave it as T1. Maybe one day we'll know it. That's good. Then T1x, so cosine, so adjacent over. Yeah, so this hypotenuse won't be the y component. It's just going to be T1. And then T1y will be the other side. So you're going to get T1x in terms of T1. Yep.
Is our angle, and then you put the line in it. So x is adjacent. So
Yeah,
this is how I
that's
put the
great.
line in.
And then
I moved the line in the
now
middle.
T1 just clarifies
So so you have our degree angle, and the one that's on the diagonal is always hypotenuse. That guy's always the hypotenuse. And since we know our angle is right there,
So then let's,
the
is
one
that
on
the
the line
adjacent?
right next to the angle is adjacent. That is x. X is a, because it's horizontal.
The key to
And
that,
then,
what angle?
you know, this is the opposite, it's opposite to your angle, and it's y, so, alright.
Yep, so then you're just gonna do the set up the equation first,
Cosine.
and you're gonna get the answer in terms of T1. Your T1x equals. Yeah.
Also,
What is opposite?
yeah, also,
Nope. You know, pretend like you know T1, pretend like you do hypotenuse. So you're gonna draw two different triangles for each of these. Two different right triangles. One of them for T1, one of them for the spring T1, like that arrow. One of them for that. So which one are you doing? Are you doing T1? Yes. Alright, so make a beautiful right triangle, like that triangle. Beautiful right triangle. Perfect. What number then you Yep, and just be careful. So you can do that, that's fine. Just know that yes, yeah, that's gonna make your life really easy. Yeah, so go through that process. Alright, so let's draw these triangles. I'm gonna draw them off to the side because it's too tight to do them here. So let's do T1 first. Do one at a time. You can't do them both at the same time. I'm going to make a right triangle. Now, I saw a lot of really, I love that I saw people draw this right triangle differently. And like the ways I saw it were correct. I'm going to pick the one with the angle that I know. So I'm going to make a right triangle that includes the angle that I know. So I know this 41 degrees. It's just convenient. If you make a right triangle with an angle you know, it just makes less work. I also saw people do this, and I thought this was great because I saw that this meant that you understand your geometry. If this is 41 degrees, then this is 41 degrees. That's that whole, I don't know, it's got some name for it if you got a thing like that. So I saw people build this triangle, and that is also totally valid. I saw people also find this angle. So this angle over here, if this is 41 degrees, this will be 90 minus 41 degrees, which is going to be 49 degrees. That's also fine. Like all of these are good, like realizing how the angles, you can move them around and find other angles, all good stuff. So I'm just going to use this one though because the angle is there. T1 is my hypotenuse. T1x is my x component. Now, remember when you draw these, you better draw these as arrows. If you just make them two sides, you're missing information. So when I draw this y component, does T1 point up or down? Up. If you all look at T1 and you had to describe it, does it point up or down? It points up. Does T1 point left or right? Left. Why does this matter? Up is positive, down is negative. To the right is positive, to the left is negative. All right, great. So T1x is the x part of it. How am I going to do this? So T1x, is it the adjacent or the opposite side? Is it the side touching my 41 or is it across from my 41? Touching it, so it's my adjacent. That makes this my opposite. We're going to pretend like we know T1. We're going to pretend a variable is just something that we haven't found the number for yet. We're going to pretend like we know it. So we're going to get T1x in terms of the hypotenuse, like we've been doing every vector problem ever. So to that end, SOHCAHTOA, which one am I going to use? Sine, cosine, or tangent, if I want to use the hypotenuse and the adjacent. Cosine, nice. So we're going to say cosine of 41 equals T1x over T1. If you rearrange that and you solve for T1x, how do you do that? You kick the T1 to the other side and you get T1 cosine of 41. Yay! Do it again for the y component. You'll instead do sine. And then if you make a triangle for T2 and you go through that process, T2 points this way. This one's 63 degrees. You draw a beautiful triangle. Oh, how lovely. T2x, T2y. You end up getting a similar relationship. T2 times cosine of 63 and T2 times, oops. Here, I'm going to make it so I'm right by changing these xy.
So it follows a similar thing. And this isn't because x is always cosine and y is always sine. It's not because of that. It's because x is the adjacent side and sine is the opposite side. Okay, great. We did this. For now, we have no idea why we did this other than anytime you see a vector, just know you're going to have to do this. Now we're going to use this in a second. Now it exists. Let's copy over all the stuff that we had before. Remember, steps 1, 2, and 3 are kind of the same. Except I'm going to make a slight modification here. So we're basically solving a new problem where instead of using weight, we don't care about, well, I guess we could put weight here. We know T3 now. How exciting. You all found T3 in the last problem. So let's build our equations, y'all. Let's build our equations. Sum of forces in the x equals MAX. Looking at my original picture here, are there any forces pointed left, right? Yeah, what forces are pointed x right or left, right? T1 and T2, but specifically what parts of T1 and T2? T1x and T2x. Oh, look, the components are... So when we build this equation, T1x, is it positive or negative? You always have to think about this. It's negative. Why? Which way is it pointed? Left. So negative T1x plus T2x, positive or negative? Positive equals MAX. Now, I'm going to go ahead and continue this one. Let's continue this equation. Man, if only I had an expression for T1x that we just found. In terms of because we don't want T1x in this problem. We want T1. If only I had T1x in terms of T1. Oh. That's what we did over here, y'all. Make the substitution. What is T1x in terms of T1? T1 cosine of 41. Don't forget your negative sign. It's easy to lose track of those. Plus, what's T2x in terms of T2? T2 times cosine of 63 equals, we don't know our mass, but what's our acceleration? So what's going to happen to that term? It's going to equal 0. All right, can we solve that? Y'all cannot solve one equation with two unknowns. Looks like we're going to have to build another equation. Oh, look, a formula to build another equation. Let's do it in the y direction. It's all about building the equations. All right, y'all tell me what forces are acting in the up-down direction. Gravity, but in this picture, we actually don't have gravity. We do have something pointed down that connected to gravity. Yeah, so we had T3. Is that one up or down? Negative T3. We don't need to break that one into x and y components because it was already up, down. Plus, what else? T1y. Positive or negative? I kind of put it here, but you all tell me whether it's right. Because which way is T1y pointed, up or down? Up. What's going to come next? Plus T2y equals MAY. What's my acceleration in the y? 0. All right. I want you all to try swapping those in. So next step, replace the T1y and the T2y. Like we did before. Go ahead and try that. No, they're actually going to be different. Yeah, they're going to be different values, and the reason is that because of the angle.
Okay.
One is going to contribute more or less. Yeah. It's a good question. It's like, oh, they sure, and that you can't use distance. So in that case, the distance is the same of those wires. That doesn't necessarily correspond to the forces.
Okay.
They're two different variables. Yeah, so it's one of those just because
distance-wise they share a side doesn't mean that the forces are.
Oh, look at that. Seven. And then I'm gonna get in the microwave and leave my lunch. On the way.
So next step is you're just gonna take these.
I know this is like the quizzes on
That's hilarious. I'm sorry. That's funny.
Yeah.
I went Like, it's a weird thing, like, really, I'm really very, very well, no.
Yes. Was it algebra problem? It's all for T1. Yeah, as long as you know what the process is. The math is the more important. The physics is that setting it up. Yeah. It is. Yep, but what's the acceleration of this? Is it speeding up or down? Yeah. No. It's 0. Yeah, and that's where acceleration is not gravity. That's a classic thing. Kinematics was like, oh, A is 9.8, A is 9.8. It is if the object is in the air. Yeah, if it's in the air and gravity is the only thing acting on it, then yes, A is negative 9.8. But we're learning that A can be anything, depending on the problem. In this case, it's A.
Obviously, it's frozen. You know, I freeze it, I freeze batches, I'll take out batches.
We still have so many unknown variables.
It's so frustrating.
All right, so there's the equation, y'all. I just swapped them in. I just swapped in the y components. So I took the T1y. Oh, look, there's an equation for T1y. T1x or T2y. Oh, look, there's an equation for T2y. Swap it in. All right. Now you have 2 equations with 2 unknowns. Now it's an algebra problem.
Oh wait, it's a system.
It's a system of equations. Is it unpleasant? Yes. And honestly, am I going to bother spending much of the time on it? So, like, I'll just quickly show you all this. I'm not going to spend that much time. Like, I don't want to. Yes, math skills are important, and I do actually encourage you to try this out because this is a skill that you all need. So I'm just going to copy these 2 equations over. So I'm going to put these over here just to organize them a bit easier because we're going to need some space. And yeah, I do want you all to spend a second, see if you know how to do this. I don't know if y'all have to do the GRE for med school or anything like that or what. No, do you have to do math? Like, is math a thing on it? Physics is on it, but do they require you to know like algebra and things like that? Just physics. Okay. Anyway, see if you all can pretend like T1 and T2 are X and Y. Like they're just letters. So I got 2 equations with 2 unknowns. See if you know how to do it. Just this is a test of your algebra skills. To give you all some peace of mind, I will not give you all a problem like this as a multiple choice. I will not give you all a problem where you're spending most of your time doing math. In general, a problem, I expect you to spend 60 to 70% of the time setting up the problem. That doesn't mean like that's a lot of time. I expect you to only spend 30% of your time at most doing the math. This problem, the math takes roughly as much time maybe as, well, this is a math year 1.
If this type of problem was on an exam, my goal would be for us to figure out.
Yeah, that's really what I tried to figure out some way of rewording this to like, yeah, maybe I would say like, how does the X components is one bigger than the other? And so you'd say, oh, they're equal to each other. Yeah, I care about more of the pieces here than this, but it is still good. The asking now class is like, okay, math is just
Just give you an utter answer. That's hilarious. I'm not saying they let's try
I mean, I guess it's all
So say I want to roll light work because it won't cancel out on you.
But it's the type of thing where you set those on top of each other and then you can like subtract or add the entire equation.
That is a thing you can do. That is a strategy. But then you gotta be kind of clever in how you do that because these ones, you have to multiply one of these. The easier strategy is the easier, more straightforward strategy is solve for one of these variables. So like T1 equals something. Right? In terms of T2. Get T1 in terms of T2 and then put it here in this equation. Yeah, it's not pleasant. It's not pleasant. Yeah.
Yeah. Oh, and then more of that.
I gotta watch my face.
This is the way I was gonna do this.
Did you have a different strap for doing it? There is other ways. There's other ways to do it.
I was just like measuring once and then doing my calculation.
The problem is they won't really cancel each other out. So you'll still be left with two variables.
Okay.
There is ways to make it so they cancel each other out. Basically, I can take this entire equation and I can multiply it by sine of 41, and then I can multiply this entire equation by cosine of 41,
I feel like I do
and then these two terms cancel each other,
Okay. Okay. Yeah.
which is a bit of a mess. That works. That is a strategy, and at times can be useful, but with these sines and cosines, it makes it a little unpleasant. So what I recommend, the more brute force method is solve one of the variables. Plug it in. Otherwise, you have to scale the equation. So when you do set them equal to each other, one of them does cancel. But it's cool that you know that strategy. I was like, that's one of those that
What is yeah, but you work put it back in.
All right, and again, because this is the least important, like this is the least exciting part of this is just math. All the physics is done. You can decide whether to solve this now or you can put it to the side and do it another time. We'll reconvene at 9:30. So like, you can take a step away from this problem. Don't feel like you have. I know it's kind of unfortunate, but I do want to give you all the break and continue stuff. So actually, I say let's say 9:33, 10 minutes from now. So you can decide if you want to finish this or just whatever, put it to the side. The physics is done. The setup, setting up the problem is honestly what I care about. I will straight up tell you, I will not ask a problem like this on the test because it has more math. I don't want math to be the reason you miss a question. What I could ask you on a test is I could give you this problem and say, how does the x component of T1 compare to the x component of T2? I could ask something like that because you don't actually need to do any math to figure that out. Or I could say, what's the value of T3? Because that's really easy.
No, it would be something related to the That's true. But would they equal out? No, they should.
Well, based on that, T1 has more. Wait,
I would expect you want to have one. Which way would it be? Like, it's like it's more towards the two, therefore, C2 would have greater access.
No, me either. No, I would do like for them. It's
Yeah,
also like.
vertical, but it's so.
Yeah, and like people can't learn that. Like if they had like, for example, like physics one, and like if you did physics 2, like everyone would be so fun.
Yes, and T1 has more on the opposite. But T1 go to the left, therefore it.
I probably would go on. I like it.
That one is them.
And I feel like back there.
There's a lot of math.
A smart thing. If your like goal is to be like the
Your mic is on. Yeah, it's blinking green.
Yeah, that's what yeah,
Some horrible thing. This is why businesses don't work in numbers. Why do we need numbers? Just like so then you'll do it. It's a system. Got two equations.
I'm debating there. I just like I don't know. I haven't been there. Is it like busy? Like is it like what's it called? Like I hated that bash because it was so slammed. Like it was where it's like the difference of like the gym. That's like like at that point, I feel like it's like universal tickets are a little cheap. Not cheap, but like it's like a paycheck.
In terms of C2, and then what that is.
yeah, but they have to be only
Oh, yes. Okay.
And then towards like the real end,
You're like not even close to
UCF people, yeah. When is the pickup thing? I'm like way too lazy. Like if I'm not on campus, what I do, I'm I got like a Disney one. Because my little sister, she goes to and we're going to got one. So then they'd be coming and staying with me anyway. So I was like, at that point, and it pays itself off if you go with people. It's like, it's like a $200 down payment, like $35 a month. No, maybe not that. I just but it's nothing like crazy. If you think about it, like, yes, if you add up the total, it's like really not a lot. But like the monthly thing, if you go like once a month, for example, like it's so cheap because it's like the ticket well, it's like for a park offer is like anyways, so like yeah, I know it is. But it's like if you like, I was thinking about it and I was like, okay, whenever they come down, I'm gonna want to go, and I have like the one that you blocked out. So like it sucks because the good weekends and stuff you're like, oh, you can't go. But those are also the busy weekends, so I'm yeah, it is cheaper. But I would like want to go for my trip first, like once I'm 21.
What did I flip here?
Which I've done before with my parents, but like I want to go.
Oh my goodness. No, that's good.
Yeah, so I was like, okay, like we'd probably do 2 days because we didn't want to drive back after, so we'd like get a hotel, whatever, and then probably go the next morning.
Oh, I dropped a term.
2 days. Whenever my sister comes, she was already planning on coming 2 times. We've been twice already. So then that's already like 4 days that I'm like just in general since I have 4 different tickets, and then so that's already $400 that passes. Yeah, it's like 500-600. So at that point, when I go an extra 2 weekends and it's already paid off. So plus I like figured I know the lots are this good, but I do like that. But like university is so stressful. I don't know, it gives me like stressful vibes. Yeah, exactly. It's like I feel like they like use the name as stressful and everything. Like there's and like also like Disney sometimes like good rides are the ones that like if you go like at night and stuff, like or not every like like during the weekends I would be having out. So it's like when I've been it's low key been like it hasn't been slept. Like I think we waited like 40 minutes for time. Like it's like you have to like know when to go and know when to like I think like okay we don't have to go on this ride today. Wait. It was like that's exactly. It's yeah. And, oh, I wanted to go to see the baby elephant. Baby tiger. They just got a baby tiger. There's this like course with like Animal Kingdom that I want to do so bad. I don't think I would choose like because my chick has because they go based on GPA and like seniority. But my GPA is only like 5.2, and you get priority for every time you apply. But I was like talking to people who applied for it, and you know, like 3 people that applied to 3.8, and I'm like, oh, I'm not gonna get it. It's only 14.
It's a pleasant, isn't it?
So I'm like, I
made a mistake.
I tried. I should have applied last year, even without this year. Just like, because I was like a 3.7 last year because I did take Orgo, Excel, or anything like that. That's why I waited for like this too. Which one is so and now she's doing it easy this semester because everyone took her class this semester. No, I'm so good. Like I was talking to like or one of my friends was friends with someone who like is taking it this semester, and the exam's so easy. Like literally like there are 3 layers in the cell membrane. How many layers are in like a part of the cell membrane? You know what the questions are when we took that exam? Name the layers of each layer of the cell membrane. Like, everyone failed. Everybody failed. It was like her first time teaching a full semester, and she offered extra credit for summer, and she didn't offer extra credit for us because the summer people cheated. And I was like, "Bro, so you're like, that's not us." Like,
all right, so I worked out the whole thing here. Honestly, again, this last part is just an exercise in algebra. I even made a mistake when I was doing this. If I was, so again, I am not going to give one this involved. I will upload these slides. So if you just don't, reminder to y'all, within a day or 2 of class, I always will upload these slides. If you go to web courses, so yeah, you're more, I was like, because I saw a bunch of people taking pictures, which is great. Like you're more than welcome to, but just note that, and that totally works if that's your preference. But I will upload these as a PDF and as a PowerPoint. If you're ever like, man, he did something and maybe you missed taking a picture of it or something like that. If you just go by week, every single week I have it organized. It's in the Files tab. And if you go to week 5, so you can see last class is here. So after every class, I upload it. The PDF is the one you want to look at because the PowerPoint's going to look all crazy. The PDF, the handwriting looks correct. The PowerPoint will look correct if you download it. But if you look in the viewer here, if you use this thing, it's going to look all sorts of kind of weird. Sometimes it's okay. Sometimes it's weird. But if you download it, the PowerPoint looks fine. And I do both depending on your preference. So, yeah, if I was doing this problem, so obviously I did this problem, but if I was like, again, I'm not going to ask one this many math steps in it, because the math is the least interesting part of the problem. If I did this though, what I would do to check my work, because that's always an important skill. How do you check your work? You all have an expression right here for T1 and T2. When you get T1 and T2, if you plug them into this expression, it better equal 0. And then you can also test this one as well. When you plug T1 and T2 in this expression as well, it should also equal 0. If they do not work in both equations, it's bad. And they might work in one equation, but not the other. That means you made a mistake. So,
What kind of questions did you say you might ask?
Yeah, so a question I might ask, if we look at this problem, what might I ask if this is, so if I asked a multiple choice problem, what would I ask? I might say, so I don't have too many of these, but it would be good if I did. It would actually, I'm going to tell you I don't have one like this, but moving forward it is, because I've already made the test. I'm like, oh, this would have been a cool one. I might ask, hey, what's the equation in terms of T1 and T2? What's an expression that relates T1, T2, and T3? So that would be this like this one here. Relate the X and Y. Like, can you build, what do I care about? I care about steps 1, 2, 3. So I'd ask questions related to steps 1, 2, 3. Hey, how does T3 compare to the T1 and T2? And this would be the expression that would work. Or I might say, how does the X component of T1 compare to the X component of T2? There is no math involved in that. When you set up this equation, how do they compare? They're equal to each other. And that's realizing however much T1 pulls to the left, T2 has to point to the right to cancel it out. So stuff like, can you build the equations? It's all about the skill set. Any problem I give you, anytime there's a numerical answer at the end, it's just to check if you did the process correctly. And as a rule of thumb, you should never spend more than, if you're doing a problem on the test, 20%, 70 to 80% of your time should be preparing the question. Only 20 to 30% should be doing the math. The math should take you the least amount of time by far. Obviously, this problem doesn't fall into that camp, which is why I'm not going to ask a problem like this. And this is also true of the free response. 70 to 80% of your time should be setting up the problem. 20 to 30% of your time should be actually doing the math. That's how the time distribution should work. That's what because the math is the least important. If you all look at the rubric, only 20% of the points, 10 to 20% of the points is getting the right answer. 80%, which remember 80% is an A, is setting up the problem. Okay, so what's the takeaways from this problem? It's not the math at the end. That's not the takeaway. That was a good reminder that like systems of equations is good. The takeaways are, can you identify where to draw your free body diagrams and the forces acting on each of those things? We had to draw 2 of them here. Can you realize that sometimes you might have to do that and the problem has 2 different free body diagrams? And then, can you build the equations for each one? Can you build the sum of forces for the first free body diagram? Can you build the sum of forces for the second free body diagram? And related to that, can you split things into X and Y components? Do you realize that that's something you're always going to have to do? That's the skills. That's the main things to take away from this problem. When you look at this problem in the future, you do not need to necessarily solve out the whole problem, but I highly recommend you get to step 3. I highly recommend you all try this and try to build the equation. And then don't worry about doing the math after. I really don't care about that. You don't need to spend the time then solving it to make. You have the solutions here for step 3. You can come and check those. That's the steps. That's really what you should be kind of. Can you build this problem? Can you get to step 3 of this problem and get that done? All right. Any questions? And this is a good kind of example of setting up a free body diagram problem, force problem, and all that jazz. Okay, let's see how good you are at free body diagrams. It's so important, I'm just going to keep asking questions about it. Which of the following is the correct free body diagram for a car at rest? And look, I even labeled them for you this time. There's only one right answer. We assume this is on Earth, right? Yes. You can assume you're always on Earth unless stated otherwise. Yeah. You're always on Earth unless stated otherwise.
Wait, is this at the core where the gravity is acting?
Yeah, where on Earth is this? Is it Madagascar where gravity is slightly more dense?
There is places on Earth, the farther away you get from the Earth's center, the weaker gravity gets. So like when you're on, if you climb to the top of Mount Everest, your force of gravity would be slightly less than if you were
at the lowest place on land. I'm not going to add water.
The density of Earth is also variable.
Yeah. And where that density, I don't know how it is, honestly.
It messes up satellites a lot.
Yeah, that makes sense.
They have to actively track them and keep track of them.
Yeah.
Because the map they have gets wrong after about 2 weeks.
Is that really how? I haven't looked into that. I do know that there's always a little bit of air resistance. The atmosphere doesn't just have to in. Like, there's not like a cutoff. Like, oh, there's no air here.
Okay,
It's
so
very
that's like
gradual, less and less and less and less. So even the satellites out there are able to. The ISS has that problem. The ISS will eventually crash because of that. They have orbital adjustments on it.
Oh,
They have little rockets on it that keep it up there. As long as they keep it fuel. Alright, 10 more seconds. This is not a math problem, so.
I used to like black holes because like you're like it's like they're even
40% of the problems in the multiple choice will be like this. No math required. If you know what you're doing, there's no math on the test. All right, 5, 4, 3, 2, 1. Always the key to these is do not look at the picture and say what's the right picture. The key to these is draw the picture and then say which one matches yours. Go make certain you're going through the steps. Sometimes when you look at the picture and say which one's correct, that actually ends up you forget things. Whereas when you go through the steps, you're less likely to forget things. So you all tell me it's on Earth. What's the freebie? Gravity. Okay, great. Gravity's going downwards. Anything else affecting this car? The normal force. How do we realize that? Well, it's on a surface. That's one way. It's not accelerating downwards is the second way. So remember, these are the little checks. Normal force is upwards. Anything else? Anything pushing this car to the right or pushing it to the left? No, that's it. That's the answer. Yay! Now, if you wanted to be spicy, you could make the argument that A could technically be correct because you could if you're pushing the gas of your car, there could be like a little force trying to push it forward. Notice that in the first picture, FA and FF are exactly equal to each other. So if you wanted to be really technical, you could argue that A, if you're pushing the gas, you could be trying. And it's kind of like I can push my bottle, but it's not moving. Like I am, you can't tell, but I am pushing my bottle right now. It's not moving because friction's opposing it, whatever. But look, I'm not going to try to be go with the obvious one. We are not hitting the gas. If the car's at rest, you can assume no one's hitting the gas in the car. Make those assumptions. All right, great. Which of the following is the correct free body diagram for a car traveling at a constant 23 meters per second? Do not ignore air resistance and friction. If this is a test problem, I would have that in here. Do not ignore.
No, that's the normal force. I mean, it's constant. So, because it's not really like you're at 80 meters.
My way of being classy, but not too classy. Uncomfortably classy. My favorite one? I don't know. The physics ones, but it's hard to find physics ones. It's not a big market for it for some reason.
Like one with a bunch of equations on it.
Yeah, I gotta find one. But that one then feels too little hoity-toity. Then people look at them like, oh, look at that person. They know all this. I like the silly, I have an paper airplane one, and I have a space one. I don't even know what the other physics ones would look like. Yeah, equations.
So it was like dressed up.
People that look at that.
It's like you're not touching like the whole stuff.
I don't want people to look at me like, oh, look at that person. They know so much. Chemistry stuff, there's some of those, things like that. All right, 10 seconds.
And like, but it's like not like smashing like hot dog. It's like princess. But like she's like always waiting to watch it.
In 5, 4, 3, 2, 1. Ka-chow. All right, how do we do this? The same exact way we did the last one. We draw a box. All right, you tell me what's going on. Gravity, always gravity. Great, what else? Normal force, that still exists. Those didn't go away. Just because they cancel doesn't mean we don't draw them. That's an important thing to remember. Just because, yeah, you're not flying up, you still draw them. We're going to see why when we get to friction. Great. What else? You are moving, and if you've ever driven a car and you take your foot off the gas, what happens? You slow down. So by extension, there is a friction. Which way is that going to go? Now, we're making an assumption here, which I didn't state. This is also a healthy assumption. If not stated otherwise, we kind of assume we're going to the right. There also wasn't any other options here of friction. So great. But if that was the case, we should be slowing down. Why aren't we slowing down? Because you're going constant. What's pushing me forward? The acceleration. What do we call that random force? Applied force is the catch-all for something that's not covered by the other ones. The gas, the tires that push the car forward, and all that jazz. Yeah. There isn't an acceleration. You're correct. Every single force cancels out here. The acceleration in the entire system is 0. Yep. So there is the acceleration in the entire system is 0, but we still draw the forces because there can be value in that. If you want to find the force due to air resistance, you can actually do this. Like if you want to find the force due to air resistance or friction, this was an experiment that one of the other high school teachers would do where they would pull his truck. And they'd pull his truck at a constant velocity, and on the string they would put a spring scale so they could measure how much they were pulling it. And then the force of friction was exactly opposite that. And then you can find the mass of the truck, and we'll learn how to connect friction to gravity and all that in a second. But there you go.
So here's a fun question. What force is pushing the car forward?
The engine. Actually, is it friction?
Yes, it is friction between the tires and the road.
Different kind of friction, yeah. When you all walk, which way do you push? Yeah, when you all walk, you're not like kicking your foot forward. And just think about it's a really weird thing. None of you think about when you walk what you're doing, but when you walk, you push backwards. What pushes you forward? The ground pushes you forward. Friction is the reason if you're on ice, that's the reason you don't go forwards. Because you push backwards, but the ground doesn't push you back forwards. But we're just going to call this applied. We're not going to make 2 friction forces here because that would be unpleasant. Calculating that is also, yeah. But it's a good point. Like, what is this applied force that we just kind of chucked in a bucket and said, yeah, it's a really good question. And that's why you need good traction on your tires. If your traction on your tires goes down, you start losing that friction. And sure, your wheels can spin, but if they don't get traction, you ain't going to move. All right, this problem. We are not going to solve this entire problem because I'm going to let you solve it. Don't worry, you're still going to solve it. Like on your own. We are going to shock and awe. Guess what we're going to do first? Free body diagram. This problem has a little trick to it. So I'll read through the problem, then I'll talk through it, and then we'll kind of break it into some pieces. 2 blocks are connected by a massless rope. The ropes are always massless because if they weren't, gross. It's unpleasant. The mass of the block on the table is 4 kilograms. I'll just label that. That's 4 kilograms. The hanging mass is 1 kilogram. There it is. And the table and the pulley are frictionless. Yay. Find the acceleration of the system. Then find the tension in the rope. And then find the speed at which the hanging mass hits the floor. Yada, yada. All right. Great. Okay. Before we draw any free body diagrams, I want to show you all pulleys pulleys are special. And the key to whenever you see a pulley
A pulley redirects forces. A pulley, that's all a pulley does. A pulley takes a force. So let's look at this one. It's right here in front of us. Which way is mass 2 going to want to go? Why? Because of gravity, right? Like nothing shocking there. That pulley is going to take that force downwards. And which way is it going to make mass 1 move? To the right. It just redirects that force. That's all a pulley does. Have you ever had like a pulley hanging from a ceiling? And say you pull down on it. Say you pull down on it with an applied force of, who cares what, 10 newtons. Guess how much this block's going to get pulled up with? 10 newtons. It redirects that force. That's all a pulley does. So the reason I mention that, this problem, there's a couple ways you can solve it, but we're going to I'm going to show you all the easy way, and that's the way I'm going to emphasize. And then I'll briefly mention the other way. Something absolute that's like going to, I don't know if it's going to break your brain, but it's going to, you might not like this. This is a one-dimensional problem. And you're going to be like, what? Which way is block 1 moving? Right. Which way is block 2 going to move? Down. Up to this point, I've told you left, right, and up, down are separated from each other. And that is generally true. But the mindset shift I want you all to think about is in this problem, it's 1D because they can only go forwards or backwards. At the end of the day, there's only 2 directions you can move. Forwards and backwards along this path. You cannot deviate from this path. Block 2 is never going to be going off this path. And so as crazy as this mindset is, 1 dimension just means you can move either forwards or backwards. That's 1 dimension. Forwards or backwards. You got a positive and a negative direction. Okay? So as crazy as that idea is, for now, just work with me on that. Just like we're going to work with that. And we're going to use that to make this problem way easier than it would be if you don't. So kind of a little like physics trick that like 1 dimension doesn't mean you're moving explicitly left, right. It means you can only go forwards or backwards. It's 1 dimensional. Anyway, there was a question. Okay. Now, that's one piece of information we're going to use. You can only move forwards or backwards. It's a 1-dimensional problem. Wild. The other one is one I mentioned before. If 2 objects move together, you should consider them together. You should consider them as 1 object. Again, weird idea. But let's just apply that to this problem. If block 2 moves down 1 meter, how much is block 1 going to move? 1 meter. If the acceleration of block 2 is 5, what's the acceleration of block 1? They're stuck together, y'all. If the accelerations aren't the same, just think about what that would mean. That would mean that the one on the bottom moves faster, and that would break the rope. And if the rope breaks, then it's not the same problem, and that's not going to happen. Again, think of a trailer and a car. If I hit the gas and my car starts accelerating, my trailer better accelerate behind me at the same amount. Otherwise, the trailer's not coming with me. And that's where actually you can tow a car with just a rope. So like if you have cars that are broken down, if you just have a rope, you can tow it. And as long as you're going at constant velocity, it's no problem. What becomes a problem is if the car in front hits the gas too hard and that puts a lot of tension on that rope and the rope can't handle that, then it's bad. You also want someone in the car behind you because when the car in the front hits the brakes, the car behind them doesn't know that you slowed down. So they also have to hit the brakes. But yeah, that's been it. If your car broke down and you're not that far from home, you are legally allowed to do this, is like tie a rope to one car and another car and like tow it yourself, just with like a thick rope. But you got to go slow. You don't want that force to be so large that the rope snaps. You want them both to accelerate together. Anyway, fun facts. Why do I know that? Because again, when I worked in high school, one of the teachers did that. He drove his car like 2 or 3 miles, just towing it with another car with a rope attached to it. Looks really jank, but it's fine. Okay. So, 2 key pieces here. Pulleys redirect forces. Pulleys redirect forces. Second one, we're going to draw these objects together. So, how are we going to draw the free body diagram? 2 blocks together. Now, and then the thing I'm going to tell you all, reminder to you all, this is a one-dimensional problem. To the right is not left, right, or up, down. It's forwards. Forwards. And then to the left is going to be backwards. Any force that is pulling it forwards points to the right. Any force that's pulling it backwards points to the left. We have pretended like that rope doesn't exist. Pretend like that rope doesn't exist. These 2 blocks are smushed together. I want you all to try to draw the forces here. There is 3 arrows you should draw on this picture. That's my hint to you. See if you can figure it out. And to do this, I will tell you, you're going to kind of consider block 1 and you're going to consider block 2 and the forces acting on them, but you're going to draw it on this picture. Try to draw 3 arrows, and you're going to draw a couple arrows on block 1 and draw an arrow on block 2. There. And if you have anything to add to this, let me know.
I'm trying to think through how to do it the hard way.
The hard way is you draw 2 free body diagrams and you find the tension in the rope.
Yeah, and I'm just trying to do them in my head.
The thing that's really the thing that's unpleasant in that's tricky, is you have to realize that block A's acceleration is positive, but block B's acceleration is negative.
But the magnitude is the same.
So when you do set up the equations, you have to swap.
I would probably do it by defining downwards positive y to make the math easier.
Which is effectively doing the yeah. So this time we're pretending like the rope is unless you decide that way of drawing it is everybody diagram. No, because we're bashing these slots. That rope, all it's doing is transmitting whatever forces are acting on the cycle, transmitting it to the person. And the whole system is coupled together. Yeah, all the rope is a linkage connecting things together. A linkage that takes a force and directs it along that rope. Alright, so what is pulling the system forwards? That's, again, when you draw free body diagrams, it's all about forces. What's going to pull this system forward? Why? It is going to move forward. Like, you all can look at this picture and hopefully tell it's going to move forward. Why? Gravity. Due to which object? Mass 2 is going to experience a force of gravity. So we could kind of draw it on here. FG, and we'll call it FG2. We could draw in this picture. Which way will it point in this picture? Up, down, left, right? Which way is forward? Right. So this is, which way is gravity going to pull it? So this is the mindset you need with these pulley problems. You got forwards and backwards. And all your forces, you got to think of lining up in that direction. So force of gravity 2 is going to pull it to the right. Notice I called it force of gravity 2. Mass 1, the force of, sure. But is there a force of gravity acting on object 1? Yes. Yeah, which way is that going to be? Because is that one pulling it forwards or backwards? No. So there is a force of gravity acting on object 1, but it's not making us move forwards or backwards. What else? There's one more arrow I need to draw here. Ooh, force of friction. We could do this problem with friction. And I think I have a quiz problem that does have this problem with friction on it. But I haven't taught you how to do that quite yet, so we're sparing you from that. But I think someone else said, what is the one that's pointed up? Normal force. Is it helping it move forwards or backwards? No. So this problem, this is the key to solving of any pulley problem. Any pulley problem, you can do this. You pretend like the rope is just something that's transmitting the force. And the mistakes that most often, so we'll set it up and then I'll tell you the mistakes that most often happen. All right. So we could write down, what are we solving for? We're solving for acceleration. If I write down my givens, I know M1 equals 4 kilograms. M2 equals 1 kilogram. We could solve for these forces. We could do that now or later. I don't really care. Go ahead and try it now. Why not, for funsies? Find the force of gravity 2 and find the force of gravity 1. Yeah. Yeah, let me move that arrow. That arrow to the left was just like showing forwards is to the right and backwards is to the left. Yeah, that one's not actually a force. It was just saying how we decide to put our arrows.
Well, his graph has
Divided by the mass. That's another trick is realizing that the mass is small. Yep, go ahead and try to find the tension now. You're going to have to draw different three-body diagrams.
Yeah. So your mass one has its gravity and
I did. I wrote that up.
It's because when you're adding it, because you're pulling it to 0. So when you're doing the negative force of gravity, it's like 53, you're adding it to 0. So then you add negative. Or like, you know what I mean when you do that algebra problems? When it's not. That's why.
All right, M times G. Very exciting. Guess what equation we're going to use for 3? FMA. Sum of forces equals MA. Always. Sum of forces in the X equals MAX. Sum of forces in the Y equals MAY. Yay! So, remember our X is the left, our forwards and backwards in this case, and our Y is whatever you want to call the other one. Is anything happening in the Y direction? No. Now, what's relevant here, I'm going to build it. Well, let's build both of them. Actually, you build them. It's fun. Go ahead and build those equations. Build both of them. X is left, X is forwards, backwards. Again, we're not thinking left, right, or up, down here. We're thinking forwards and backwards. And Y is whatever the other, not forwards and backwards.
So that would be -1.
FT2 is forward. And FT1 is backwards.
So,
Wait, no.
what direction did I point?
No. We're going to find that out in part B. Don't worry about it. So right now, tension didn't show up anywhere here because we pretend like a rope didn't exist. We pretended, so basically this rope is just taking whatever's happening here and kind of extending it to here. So we're basically taking this one, slapping it against this block, and then saying, why is this block moving? Because the gravity's pulling it down. So we can basically pretend like this block is here, and then that gravity's
A0, so we're searching for F.
and it's the same type of
But I'm assuming that since the only thing pulling it right is gravity.
It's a weird.
Then I'm pointing how.
Okay, yeah, maybe part B. So tension, you're gonna have to draw the right, draw. So this will put the blocks together, and tension is.
Maybe
Because tension pulls this block to the right, and this block to this way.
Except your mass
is there is still like,
Tension pulling this one
or maybe
backwards,
it's only going
tension
forward
pulling
and
this
going
forward, so they
If that's what
cancel
we're
each other
doing,
out.
it's one
Just didn't even
dimensional.
put it in the picture.
So Y would be like
But
up or
you
down,
need
but even though
One of
it's
us, yeah.
Someone had a good point. If you wanted to draw tension in this picture, which way is tension pulling block 2? Forwards or backwards? Backwards. Which way is tension pulling block 1? Forwards or backwards? Forwards. What happens to those two things? For every force, there's an equal and opposite force. So in this picture, we kind of ignore tensions because we combined them. So anyway, that's if you're curious there. All right. Y'all tell me what forces are acting in the forwards-backwards direction? FG2. Anything else? Nope. What's that going to equal? Well, what's the right? So MAX. What's the mass of this object? Is it 1? Is it 4? Or is it something else?
The one with gravity being pulled
You add them together, y'all. If I put my blocks together, what's the mass of them? M1 plus M2. You have to move both of them. They're together. My system, my picture I drew, it's always the mass of that entire system times A. And then forwards, backwards. In the y direction, what forces do we have?
Gravity and normal.
Gravity and normal. Which way is normal? Great, positive. Which way is gravity?
Negative.
Down. What's my acceleration in this, like, whatever direction you want to call this thing? 0. It's going to be, it's still M1 plus M2 times AY, but AY is 0. Why is this useful? You can use this to find the normal force. Why is that useful? We're going to find friction, you need the normal force. We're not going to do that for this problem. All right. Copy all the goodness to the next slide. I want that little thing. All right. So yeah, this problem, this is the trick to this one. This is the trick to any pulley problem. Okay, so let's write that out. Step 4, that means, you all go ahead and try it. Actually, I'm not going to write any more. Like, you all try to solve for the acceleration. It's all, we built the equation. That's the hard part. Now you just got to plug in the numbers. Oh yeah, the first thing I said on the side definitely. I still haven't quite ironed out that one. I still have to figure out. That's my acceleration. In this context, which way is it? Down, so acceleration. Yeah. So, wait, no. So if I minus the F then would be
your rope tension is the exact same.
So be negative 9.8.
And then this, yeah. So it won't be negative 9.8. It'll be this.
So I guess
Well, it's I was like, that's fine. I just make that exact decision before. I don't really care what that.
I think he rounded. Because your answer is what I got when I went to.
All right, so just to write this out, FG2 is going to be 9.8 equals my mass 1, which is 4, plus 1. So we get AX equals 9.8 divided by 5, and that equals 1 point something. 96. Great. And it's positive because which way is it going to move? Forwards or backwards? Forwards. Yay. So in this context, each block is going to get that acceleration. Oh, and someone had a good question. How to refer to me? Dr. James, Professor, whatever. You can call me any of those. You can also just call me by my first name, Wesley. That's fine as well. I don't really, whatever you feel more comfortable with. I don't really care. As long as I know you're referring to me, I will come over. So, all right. If we want, we can build the equation for the second one just to show it. We're not going to use it in this problem. But if you want to, Fn plus negative 39.2 equals 0. Hey, the normal force is 39.2 newtons acting on object 1. Only on object 1. There's no normal force acting on object 2 because it's not sitting on anything. You don't need to do that. That's just for funsies. Okay.
So if you wanted to do this the hard way,
we're going to see. Yeah.
You could set up a free body diagram for each. And then you still know that the magnitude of the acceleration is going to be the same. So you'd have two equations, two unknowns, the tension and the acceleration, and you could solve it that way as well.
And you may be like, why would I do that? Well, let's look at part B. Find the tension in the rope. Hey, guess what? Does this picture have tension in it? Now. So we need to draw a free body diagram with tension in it. There's two possible free body diagrams you all can draw. Either one will get you the right answer. Find where tension acts in this picture and draw. There's two different free body diagrams you can draw that will let you find tension. Are you wondering like this? So tension exists in this picture, but they cancel out in this picture. In this free body diagram, the tension's canceled out, so we can't use this one. Pick a spot in the picture where tension doesn't cancel out. If you all solve this problem, there's two different things you can look at that tension is acting on. See if you all can draw them. And you can still work in the forwards and backwards mindset. You can still work. In fact, let's stay in that mindset. So when you all draw your free body diagram, work in the forwards and backwards mindset just to keep things aligned so that we're not like bouncing back and forth. That's going to make our life easier. Backwards, forwards. So yeah, where in this picture does tension show up? Focus on just that part. And draw the free body diagram for that. That's a good question. If we did 2 blocks, tension disappeared, so we can't use that one anymore. So pick a new spot in the problem, a new way to frame this problem.
So when I do this,
Well, no, for block one, instead of going forward, with the other block, it would be the tension. Yeah,
Yeah, so what happened here?
That's why I just put it All right, where did you all choose to zoom in on? Where does tension act in this picture? Where do you all see tension? M1 and M2 are both experiencing a force due to tension. We're going to do both of them. You don't need to do both. You can do either one. Let's draw M1, just M1 by itself. Great, here's M1. Here's mass 1, object 1. You all tell me, we're working in the forwards and backwards mindset. Forwards and backwards mindset. So the right is forward, left is backwards. Is there anything pulling it forwards? Tension. So which way is tension going to point? Right or left or up or down? Because that's forwards. It's going to pull it forwards. Anything else acting on this? Gravity. Anything else? Normal force. This is one way of solving this problem. You may be like, how are we going to do it? You'll see it. Fama. How are we going to do this? Fama. Look, let's just do it. Sum of forces in the x equals max. Sum of forces in the y equals may. It's always the same, like it always boils down to the same process. This problem, the only trick was realizing we're going to work in forwards and backwards versus left, right, and up, down. All right. The y direction, or the x direction. Let's set that one up. What's pointing in the x direction? Or sorry, what's pointing in the forward? Yeah, forwards and backwards direction. Just the tension. Great. Equals max. We're solving for the force of tension. We don't know that. Try it, y'all. Solve for the force of tension.
We're doing the block.
Doing that, yes. Sorry.
That's
No,
one.
that's Wait, no, we did find acceleration. Acceleration is 1.96.
Oh, yeah. Pulses was 1.96. Yeah, yep. It's acceleration block 1, it's acceleration block 2, it's acceleration both together.
I'm not sure that would be.
Yeah.
It's still oh wait, it might link those.
Yeah.
It's all about.
There's like a box right on that corner.
Oh, really?
That's
Okay.
Okay,
So it's like 8 floor.
No.
What's the math?
I did do my math wrong.
The math of this
Your math is right, and my math, which I erased, is wrong.
Okay.
We're gonna do that one next. We're gonna do the object 2 and get the exact same. Yep, instead you can look at object 2. If you all looked at object 2 and you made a free body diagram of that one, I'm gonna solve this exact same problem again with object 2 in a second. You can do it either one. There's 2 ways to get this answer.
Oh.
And they both get the same answer. Every force, there's an equal and opposite.
So mass is the one block, be 1 kilograms, times our acceleration, which is 1.98.
Mass of 1, I think, is 4 kilograms.
Oh, sorry, I meant mass of 2 is 1.
Yeah.
So how does the mass of 1 times by the same acceleration lead to the same mass?
So the free body, try to draw the free body diagram for object 2 with forwards and backwards. With forwards and backwards. All right, so the mass of object 1 is 4 kilograms times our acceleration, which is 1.96. And that equals a number. 7.84. Someone else get that as well? Great. That's the one way of checking our work. All right. Sum of force in the y direction. We're not going to use that, but just to remind you all, this one is just going to be Fn1 plus negative Fg1 equals 0. Oh, look, the force, it's the same thing you all did before. Whatever. Fantastic. All right, so I told you all there's 2 ways to do this. That's one way. This is one way to solve the answer. We can draw a free body diagram of object 2. But hey, we got 2 objects, both experiencing acceleration. I want to challenge you all, draw the free body diagram if you haven't already for object 2. Where? To the right is forwards. To the left is backwards. Right is forwards, left is backwards. Stay in that frame of reference. Stay in that kind of coordinate system.
Exactly. And then that's it.
Oh, yeah.
Because there's no, it's like 3. So it's just like 2.
Maybe.
So
Negative.
The last question.
Yeah. So that's good.
Oh my god, dude. What's the tension plus force?
In this case, they'll make to the right forwards and left backwards. There's a reason why, like, if you do down and up, it works. But you have to do something subtle that's easy to miss. Yeah.
But with the tensions, so the tension.
Yes, yes. And there's, I'll show it that way, the other way, of like up and downs. And there's a little subtle thing you have to do that is easy to miss. All right, what's pulling it forwards? Gravity. Which way is gravity going to point if it's pulling it forwards? To the right. Remember, we're saying to the right is forwards. There's a reason we're doing this. Look, I will do the up-down one in a second, and that works, but there's a subtle thing you have to do that if you don't do it, you'll get the wrong answer. What's pulling it backwards? Tension. Anything else? Anything making this thing sway not forwards and backwards? No. That's it. Make our free body, sum of force in x equals max. All right, gravity is pulling it to the forward, so we call it positive. Gravity is pulling it forward, so we're calling it positive.
In this reference frame, that's how it's going to go. What about tension? Forwards or backwards? Backwards. Equals mass times acceleration in that direction. What's my force of gravity? We already found that. I'm not going to recalculate it. It's 9.8, positive 9.8, plus negative force of tension equals 1 times the acceleration is not 9.8. Do not put 9.8 here. What's the acceleration of this object? This is a classic mistake people do where you mix up something's in the air. Oh, its acceleration is 9.8. Not if it's being pulled by other things. That's only if there's just gravity. So yeah, then you do the math. Force of tension is going to equal 9.8 minus 1 times 1.96. And you get something that makes sense once you see it. Oh my goodness, it's the same answer. Wild. Why is it the same answer? Because for every force, there's an equal and opposite force. Okay. So I'm going to show you all. This is the way I recommend doing these problems. Forwards and backwards. I'm going to show you all. If you decide to do up, down, what's going to happen? There's a decision you have to realize. There's something you have to realize. So if instead you all decided to do this, force of gravity is downwards, tension is upwards, that's fine. Totally can do that. But you're going to run into a little bit of a... And I'm going to write this. I guess I'll put it on the next slide. And just as an extra thing. But then you can't see this stuff. Where am I going to put it?
In the yellow box.
Yeah. In the yellow. Oh, yeah, sure. Why not in the yellow box? Why not, right? All right. FG2 and then tension. If I build this F equals MA, so sum of forces equals MA, and I say, oh, tension is positive, gravity is negative, great, living the dream. And I say force of tension plus, and I put in the force of gravity here, that's negative 9.8, equals, the mass is 1. Here's the subtle mistake that people will probably make. What value do you want to put as the acceleration here? It's going to be the same value. Positive or negative? Negative. It's very, if you all set this up and you put the acceleration as positive, it's wrong. Why? Which way is this block going to move? Up or down? So if you all set up and you change your kind of frame of reference, now you got to put that as negative, and that's very easy to forget to do that. When you found acceleration before, you found it as a positive because we defined forwards and backwards. When you all now change your reference frame, when you all now change your coordinate system to up and down, everything down is no longer positive. Down is now negative. Whereas in your other reference frame, down was forwards, and that's positive. So whatever reference frame you all pick to work in, stay in it. Don't swap between up and down and forwards and backwards. Otherwise, I can almost guarantee you'll forget to put this negative. Like I say, almost guarantee it's pretty easy to do because it's a subtle little thing. It's a subtle little thing you got to think about. Anyway, all right. The rest of this is just a let's see if this made sense to y'all. So this is a problem that over 2 semesters now I've tried to figure out how to better teach, and so your all's is my newest iteration. But let's see if this makes sense. So previous ones I did a couple stepping stones and whatever, so that's where this problem comes from. But how does A1 compare to A2? A1 is the acceleration of object 1, A2 is the acceleration of object 2.
Because we just found the potential.
This UCF bot needs to shut up about the course I never did.
No, I like that. That's a good crazy. I like that.
we're having a top hat tech issue.
Oh, fun.
They're doing that.
Close it and reopen. Classic, right? And if it doesn't count the point, just don't stress it. Yeah, always these things happen. Like that happens. Signals drop, things drop.
That's when you get like a job where that's fair, but also
But
like
you want to bring yeah. No, that's good. Yeah, it does.
it can be rough.
No, it means the tests are worth more of your grade if that happens. Yeah. Don't worry about it. If it doesn't work, just and I'll give you the points. Like, don't stress it. All right. We'll go. I'll just leave this one open. So this, no matter what, everyone can get this answer. All right. You all look. Let's just look at the answers. How do they compare? Yay! They're the same. Remember, they're a coupled system. Coupled meaning they're literally attached to each other. If you didn't answer the same, you can still change your answer. I'm going to leave it open. But yeah, this is, and that's why we could just stick the boxes and stick them together. So, anyway, pulleys, what's the takeaway from a pulley problem? It's like all your other force problems. The only little, trick to it is you got to think of it in forwards and backwards. Forwards and backwards, and you smash your blocks together and pretend like there's not a rope there. You can even do this if there was a system like this with a pulley going up and a pulley like an object like this. You would do the same thing. You would do forwards and backwards. And so in this problem, you got a force of gravity 2 and you got a force of gravity 1. So how would you draw this one? You'd have a force of gravity 2 and you'd have a force of gravity 1. Every single pulley problem, this is the trick. So a pulley just redirects a force. And so we just then work in this new kind of coordinate system where there's no up and downs per se. It's just forwards and backwards. Pulleys are really cool. That's the reason they exist. They let you, I can pull sideways and make something go up. I can pull down and make something go up. Or something could go down and pull me up. Like, that's the reason pulleys exist. They let you redirect forces. Which makes sense when you worked with a pulley, but within a physics context, this is how we're going to do it. Okay. Forwards, backwards. And if you want to, you could say forwards is the other way and backwards is the other way. As long as you're consistent. All right. Great. Look at that. More pictures because this problem is normally a doozy. Okay. So, spring force, I'm going to kind of zip through. Spring force, great. It's here. We're not actually going to, I'm going to straight up tell you there's not going to be any question on the test involving a spring. Not for any reason in particular. It just happened to be that way. And yeah, there you go. It's nothing fancy. It's just, hey, there's the equation for it. So I'll mention this. We will do energy and springs later. Springs, they make forces. If you ever played with a spring, you squished it and then it flew out of your, if you ever played with your pin, it's got the spring in it, you squished it and it flew away from you. Forces, right? Slinkies, all that jazz. Springs, every single spring has a spring constant. Your all's lab on Thursday will be finding the spring constant of a spring. You'll do it with a free body diagram and then you'll do it with a different equation. The bigger the K value, the more stiff a spring is. So if you have a garage, or if you've ever lived in a house with a garage or seen a garage or whatever, there is a big old spring in those garages that provides some tension to keep your, I'm trying to think through the logic of why that spring exactly exists.
Offset the weight of the door.
Oh, there you go. Nice. Okay. So offset the weight of the door. That's the reason the spring exists. Now, these springs are super stiff. You're not going to be able to stretch these springs because the weight of a garage door is quite a good amount. They have a really high K value. That's the reason I mentioned that. Really, really high. These values of K can go from 1, 2, 3, 4. Maybe you have 1 in your pin. That's really low to tens of thousands or even higher depending on the application. This spring constant, let's just look at the units. Newtons per meter. What does it reflect? It says how many newtons do you need to apply to compress it 1 meter. That's what the units represent. A spring constant of 1, if K equals 1, let's just think through the logic here. If K equals 1 newtons per meter, it means I need 1 Newton to compress 1 meter. That's literally all the spring constant means. How much force is required to compress it 1 meter? That's what the value means. You don't need to know that, but it helps. Great. There's the equation, F equals Kx. Very exciting. This applies both directions, squishing a spring or stretching a spring. Ideally, when springs are designed, it works both ways, though that's always a iffy thing. All right, we're literally just going to do, I say I have 2 questions here, but... All right, great. Literally, this is the only question we're going to ask about the spring. A spring has a spring constant of 50 newtons per meter and is stretched 1 meter. What is the force caused by the spring? Mm-hmm. Oh, I said meter?
Yeah.
Oh, stretched 1 centimeter. Very, very important. The spring has a spring constant of 50 newtons per meter and stretched 1 centimeter. What is the force caused by the spring?
Like I'm converting.
A centimeter is 100.
Yeah.
I do my zero like a real man. Exactly.
Spring constant.
Basically the same thing.
All right, we'll go like 20 more seconds.
I know how
All right. In 5, 4, 3, 2, 1. Ka-chow. All right. So one day that'll. All right. Never can close it. Oh well. This is K. This is delta. This is X. How much you compressed it, but we're gonna immediately convert it because centimeters is not what we work in. And F equals Kx, which equals 50 times 1 e to the minus 2 is the exact same thing. I'm going to write it both ways. 0.5 newtons. Yay! So great. That's the math way. Logic-wise, the spring constant of that means it takes 50 newtons to compress it 1 meter. Like, if I want to compress a spring 1 meter, I need to push with 50 newtons. If I only want to stretch it 1 centimeter, I need way less force because it's not as far. It's not as hard to do that. So, great. Very exciting. How'd we do there? Pretty darn good. All right. Another very challenging question for you all. If I push a box on a frictionless surface with no air resistance, what would eventually happen after you stopped pushing the box? Would it stop, speed up, slide forever, or who can really say?
Who knows? What if it runs into something eventually?
That was a saying when I was in grad school. Whenever we'd ever work through something. You sure? Who can really say
It
it?
doesn't say there's nothing going on in the infinite plane. There could be a building.
Oh my gosh.
Assume no building.
Yeah. Assume no other crazy.
Eventually it'll hit the edge of the universe and you're
It would slide
Yeah.
It's so weak. There will be 40% of the problem I use something like stuff, things like that. So 40% will be like these clicker problems where there's like no math involved. Now something might look like there's math involved. Well, so yeah, like I've given you all problems like what's the velocity of the ball at the highest point? I toss the ball up 10 meters per second. How fast will it be going at the highest point?
Yeah, it undergoes spaghettification. Looks like spaghettification. When you go. So stuff like that. The gravity is so strong, your feet are much more significant. Like,
All right, 5 seconds. 5, 4, 3, 2, 1. Ka-chow. All right. Newton's first law: an object in motion remains in motion until things keep doing what they're doing until something acts on it. Yay! Let's see how we did here. Going around, I heard it seemed pretty good. Yay! Fantastic. So then the follow-up question is, what's going on Earth? What was the key phrase here that made it so that it did keep going forever? Oh man, what if there was friction? Look, friction's not that bad because it's stuff that you've been doing. How do you calculate friction? You find the normal force and you multiply it by mu. Mu is just a number that I'll give you. So, friction force is the reason things slow down. It's a force. How do you label it? F with the little f next to it. How do you calculate it? You find the friction force, which is something we've been practicing. That's why I've been setting up that whole F, like the Y forces, even when it didn't matter, just to remind us. And you're just multiplied by this coefficient of friction. The coefficient of friction is something that is actually you all did that last class. Finally, we got there. Coefficient of friction is based upon what two materials, and it's actually really complicated. You can't really predict it per se. You got to calculate it, measure it, and all that jazz. The bigger the coefficient of friction, the rougher the surface, the rougher the interaction. It's always opposite direction of motion, and there you go. If you can find the normal force, if y'all are cool with that, you just multiply it by this number, and you got the friction force. So that's going to come up in problems moving forward. And the reason for friction is every object is bumpy. Even if you got to the atomic scale, what are a bunch of atoms with a bunch of sphere-looking things which are bumpy and they interact with each other? And yay. Even a surface that is like a perfectly smooth layer of atoms is bumpy because the electron clouds and things like that. So everything's bumpy. Yeah, why things are more frictiony than others is a really interesting thing, and that gets to molecular forces and how they connect to each other and all that jazz. An interesting question is why is water slippery? It's really complex. It's not an easy answer. Why is ice slippery is actually not an easy answer. I think the general thing is that it turns to liquid, but I think it's more complicated than that. Anyway, friction, complicated. All right, question for you all. Haven't taught you this. Take a guess. Is it harder to accelerate a box not moving or one that's already moving? And I'm straight up telling you, I haven't actually given you enough information currently to answer this, but so take a guess based on your experiences in life. Based on your experiences, what's the reason for this? You'll probably get the right answer, but maybe not for the reason why you're asking.
But if you're moving something that's already moving, which one was higher?
Oh, harder.
Yeah. And then a gas line that's completely like it's very like this to this to this. It's not really much.
I might need to go do it. I don't do this. I might need to go do that. It's very long.
There's technically the 1.3 code. But you don't have like a. I mean, you do have non-Newtonian fluids.
Anyway, all right, 5 seconds. 5.
They're also usually not one nice and neat substance. They're usually a mixture.
Yeah.
And 3, 2, 1. All right. Now, according to Newton's laws, the answer should be it doesn't matter. Like Newton's laws does not tell us the answer to this. Newton's laws doesn't say that it's harder to move an object that's not moving or harder to move an object that is moving. Nowhere in Newton's laws is velocity. Velocity doesn't show up in anywhere in our equations for forces. So then, okay. But the answer is it is not moving. It has nothing to do with Newton's laws, though. Kind of, sort of. What does it have to do with? This is what you all did in the lab last week. Remember, there was 2 different coefficients of friction. Static and kinetic. And the static coefficient you all hopefully found last week was bigger than the kinetic. So if you all remember that the friction force is mu Fn. Fn does not depend upon how fast you're going. So as mu goes up, friction force goes up. It's harder to move things. Why is this? I may or may not have gotten to you with this. I may have talked about it. The easiest analogy I give is with my hands. When your hands aren't moving, your fingers are rough. They're bumpy. Your fingers, when you put them together, are a bunch of bumps. When they're not moving, then bumps nestle into each other. The bumps get kind of nestled into all the little crooks and valleys, and they can get kind of stuck in those little crooks and valleys. When your hands move fast, though, they kind of skate over each other. When your hands are going fast, all the little finger nubs kind of go over each other, and they kind of skate over each other, as opposed to nestling into each other and getting kind of stuck. So static is they get stuck together like that. Kinetic, it's kind of like going over a speed bump quickly. If you're like a bunch of speed bumps in a row, if you go really slow, you're going to go, and you're going to have to go up and down over each one. Whereas if you go over really quickly, you kind of just skate over the bumps. It's kind of like if you're in the ocean, same thing. If you're going really slow in the ocean, you're going to go like over and up and down, and that's a lot of work. But if you go fast, you kind of like cut through the waves. Yeah, on some level. If the waves are so big that you're not going to cut through the water, you're not going to cut through the water. You are just going to plow into a wave, and the wave will win, and be very bad for you. So anywho, all right, I'm not going to worry about this. I'll just give you all the answer. I'm not going to test it to you. Fun fact, the way tires work, even though tires are spinning, for you to get pushed forward, it's static friction. The reason is when the tire spins, the point of contact, if it slipped, then it'd be kinetic. Hopefully your tires aren't slipping. So whenever we talk about kinetic friction, it's a slipping thing. Things have to slide over each other. Your tires should not be sliding. That would be very bad. If your tires are sliding, you've lost traction. Your tires are actually like the point of contact. If you looked at it in slow motion, the point of contact is stationary to the surface. Yeah.
Is that what causes like curves to like hydroplane?
Yeah, when you hydroplane, you lose that grip and it slides, and slides is bad because that means you're not in contact with your friction ain't doing nothing. If you're sliding, I guess friction is doing something. It's slowing you down, but you lose the control.
When you're hydroplaning, isn't it like the layer of water, and so your tires?
Yeah, you're not even touching the surface. Yeah, you're not even touching the surface anymore. Your tires have grooves in them, not just for traction, but also to divert the water away. When you're going in, that's why your tire has grooves in it, is actually to also move away water. All right, here's some coefficients of friction. They're different, and notice that they depend upon both materials. Just like last lab, you had your wood block and the metal ramp, and yeah, it varies based on both materials. All right, next class, what are we doing? What's left over? We're going to do a problem with friction. It's going to be a fun. It's not that complex. It's not that much extra. That's the last. That and we're going to do inclined planes. And what I'm going to try to teach you all is that an inclined plane is a flat problem if you turn your head sideways. If you just rotate your reference frame, remember like we did, oh look, it's flat now. And this is where I said you got to break gravity into the down and that. So that's the last two things, y'all. Friction and inclined planes we covered. Come on. Free body diagram. Come on. Pulleys, redirect forces. That's a summary of class. Oh, fun.